NJ4Z here. Welcome to my ham shack, and today on From the Ham Shack with NJ4Z, we're going to talk about antenna fundamentals. So this is the first video in a multi-part series. We're going to cover electromagnetic waves and fields today, and then we'll move on from there. So let's get started. Okay, so let's get started with the basics and the fundamentals of electromagnetic waves and fields. Okay, so I'm going to change my screen here real quick, bring this up, and now you can see a picture here. And what we have is we've got a wire that is carrying a current, which is DC power, okay? And it forms a magnetic field. When we have current moving through a wire, magnetic field will form around that wire. And it's a static field. It's called an H field, okay? Now, the difference is when we start talking about radio frequency and emitting RF from our transceivers, we are talking about an alternating current flowing through a conductor. And what that's going to do is it's going to induce a magnetic field, but that field is going to be an alternating magnetic field in relation to the alternating current or electric field that we have. So we have an E field and an H field, just like we did in the DC, but at this time, these things are alternating, okay? So the voltage along the E field is going to climb and fall and go back up again over a period of time. And also the magnetic field is going to vary, and those are related, okay, in amplitude. And when we talk about them moving, we talk about them moving in vectors. They have amplitude and direction, okay? So there's two components. It's just not a direction with a electromagnetic wave, okay? These two fields are going to be perpendicular to each other, okay, at 90 degrees, okay? They are also coupled, so you can't separate one from the other, okay? If you have an alternating current in a wire, you're going to have an alternating magnetic field, okay? If you have an alternating magnetic field, you're going to have current induced in a wire, right? They are coupled. They don't exist without each other, okay? Again, they travel at right angles to each other, and they'll move in counterclockwise or clockwise ways. It determines on how that wave propagates and what direction it's moving. They're made up of an infinite number of wave fronts. We'll talk a little bit about wave fronts a little bit later, but just know this is kind of the same thing over and over and over and over and over again, infinity, as long as that wave is moving, okay? These two fields, again, they're coupled, so they move in unison, and they move at the same speed, okay? And that speed is the speed of light through the medium which they are passing, okay? Now, that sounds like odd phraseology, but we have to make it that way, okay? Because things are not always equal when you're passing through different types of materials or mediums, okay? So when we talk about the speed of light, okay, traditionally everybody knows it as the letter C in equations, famous equations like E over mc squared, okay? Einstein's theory of general relativity, okay, or special relativity. C is the speed of light in a vacuum or free space, okay? Light travels very quickly, so over 1 second, light will travel 300 million meters, or 983,600,000 feet. I said it was fast, okay? All light and electromagnetic waves, and light is an electromagnetic wave, they travel at that same velocity through free space, okay? Now, when we get into something different, say glass, water, another type of medium, there's resistance to the wave passing through, and that's coefficient of, or dielectric constant of that material. I'm sorry, not coefficient, dielectric constant of that material. It's represented as K, okay? So just realize light doesn't flow through different mediums at the same speed, okay? In free space and in a vacuum, it's always the speed of light, c, okay? When you talk about other mediums, it's going to be a percentage of c, okay? And when we get that percentage, or the velocity factor, is 1 divided by the square root of k, which is that dielectric constant, okay? It's always a real number, okay? So it's always between 0 and 1 because it's a percentage. If you have a c or a velocity factor of 1, that means you're in free space or vacuum, okay? If you have a velocity factor of 0, you're in a black hole and not a good place to be. So anyways, just know it's between 0 and 1. And this velocity factor is going to be specific for an application, a medium, a cable, okay? So just know that not everything travels at the same speed, okay, unless you're in a vacuum or in free space, okay? And we use this velocity factor later on down the road to talk about electrical lengths of cables. So just know the velocity factor is important and how it's what it is, okay? It's the percentage of the speed of light through which the electromagnetic wave is propagating through a medium, okay? So let's talk about frequency, okay? We all know electromagnetic waves are made up of a multiple part of wave fronts, okay? And those wave fronts, basically it's a wave form, okay? And you're looking at it from an end, you have a wave front. But one oscillation of that waveform, okay? So we talk about one oscillation of waveform, so 0 to its peak amplitude, back to 0, to the negative peak amplitude, back to 0 again, is one waveform, okay? How many waveforms that wave repeats through a period of time is its wavelength, or its frequency, excuse me, its frequency, okay? So for our purposes, we use 1 second, and we measure in hertz. So one waveform through 1 second means 1 hertz, as the diagram shows you. And as we add more waveforms, the frequency increases. So now we're at 5 hertz, okay? So that's 5 waveforms per second, okay? We express this in our mathematical equations as a symbol, italics F, lowercase f, okay? So you hear me call it F, it's frequency, okay? And again, this is time flowing this way. This is our waveform on here, okay? Just know that frequency is the number of times that waveform is repeated in 1 second, measured in hertz. Now, frequency and wavelength are related, okay? So wavelength is the distance of one waveform over one waveform, how far it travels in free space, okay? Again, we're talking about free space, so we're talking about c, the speed of light in free space or in a vacuum, okay? So we want to know how far that wave propagates in one waveform, okay? So when we talk about wavelength, we're going to talk about the Greek letter lambda, okay? And lambda looks like a funny bent L, I guess. That is the symbol for wavelength, okay? And the wavelength of a specific frequency can be determined by its velocity in free space. So we come up with the equation lambda equals c over f. So that's wavelength equals the speed of light divided by the frequency. Okay? Should make perfect sense. It's how they're related. It's all by the speed of light. Okay? Now, frequency and wavelength are inversely proportional. Okay, and this becomes very important. So the higher the frequency of the wave, the shorter the wavelength. Okay, so as many times as that thing repeats itself in 1 second means those waves get ever shorter the faster it repeats itself. It won't travel as far in one wavelength as it would in something saying that it would repeat itself 1 time through 1 second, okay? So if we have a 1 hertz wave, we can tell that that would be a certain wavelength versus something where we have a 50 hertz wave. Okay, so if you look at this diagram, these two waves are propagating. Okay, these two red dots, although they're moving at different speeds, are same plane vertically. Okay, in this drawing, they are not moving in either direction here laterally along that wave. They are set at a vertical point here. They're not moving laterally. Okay, all they're doing is tracing the waveform. This one looks like it's racing along, and this one looks like it's pretty slow, but they're at the same point in time. Okay, so again, higher frequency, we have a smaller wavelength. Lower frequencies, we have a longer wavelength. Okay, that's how they're related, and you can figure out again the wavelength of a wave of a electromagnetic wave by taking the speed of light divided by the frequency. Okay, that leads us to a big equation. Okay, and when we deal with big numbers, it's always tough to do things in your head or on a calculator because you're punching a bunch of zeros. So if we take the speed of light in a vacuum for meters or in feet, and we divide it by the frequency in hertz, we get how long the waveform is, or one waveform is. Okay, we can shorten this formula, all these numbers, because we're dealing in hundreds of millions of feet or meters per second, and we're dealing in frequencies that are millions of hertz long. We can divide the entire equation by 1 million, okay, and with the numerator and denominator by a million, and we come up with a simple formula of 299.8 divided by the frequency in megahertz. Okay, so if this is 7,150,000 hertz, it's 7.150 megahertz. Okay, we're just dividing this by a million, we're dividing this by a million, so those gives us that trick of math gives us two very easy formulas, whether you're using meters or imperial measurements in feet. Okay, for me, I tend now to do everything in meters because most of the world operates in the metric system, and we use all our bands in meters, so it's a heck of a lot easier for me to try to figure out this formula than take this formula and divide that by 3.028 to go from feet to meters. Okay, yeah, can you imagine somebody calling CQ, CQ, CQ? This is the 137 foot band calling CQ. Yeah, that doesn't make any sense, right? I mean, you could do it and you'd be technically correct, but for that matter, you can call out CQ, the 2.08 chain band, or CQ 0.208 furlong band. Okay, and for those of you who are going, what the heck's a chain or a furlong? A chain is actually a measurement, and I think it's 66 feet, and a furlong is 10 chains, so it's 660 feet, and you can do the math from there and see why I came up with 2.08 and 2.8. But just being facetious there, we call things out in meters, so I tend to use 299.8. Some people round it to 300. I'm a little stickler for having proper numbers, so 2.998 divided by frequency in megahertz gives you that. But remember, this formula is super important, right? We're going to use it a ton. Very few parts of this lecture series or any of the math we're going to do, or any of the math you're going to do when you're building your antennas or designing your antennas, you're going to be using this formula. Very, very few times will you not hear wavelength, frequency, phase. Okay, those things are all going to be in the lexicon from here on out. Okay, which brings us to phases. Okay, waves and phases. So what is phase? Phase essentially is time. Okay, when we talk about a waveform and wavelengths and frequencies, okay, if you see our sinusoidal waveform here, right? When you talk about wavelength, you're talking about the distance that travels along this axis, okay? So if this was one waveform here, we could use our formula to determine how long this waveform is in distance. Okay, talk about frequency, we're talking about this as time. Okay, that's where phase comes in. So your frequency is how many times this waveform repeats itself over a given space of time, 1 second. In our case, if this was a 1 second time period, we would have something that repeated itself 4 times, right? 1, 2, 3, 4 times. So we would have that's 1, that's 2, that's 3.5 times. Excuse me, I knew that wasn't right. 3.5 times. So our frequency would be 3.5 hertz if this was 1 second. Okay. So we talk about phase. It's a relative measurement of time between or within waveforms. Okay. I know that kind of sounds weird, but let's just look at it. Okay. So here and here and here are the same points on the waveform at a different point in time. Okay. So we come up here and we're here on this waveform, come up here and we're here on this waveform, come up here and we're here on the waveform. So you can see all 3 of those points, A, B, and C, are at the same point in the waveform at a different point in time. Okay. The next diagram becomes a little clearer if I show you this. Okay, again, A, B, and C, same point in the waveform over a different period of time. Okay. Now we have a second wave here, and this wave started earlier than this waveform. Okay. So if this is the same period of time, this wave's down here at the bottom of its cycle and coming back up. So its waveform is actually here. Okay. And then it goes again, repeats here, and goes again and repeats here. This one starts at 0, so when it gets back to 0 the second time, its waveform's there. Okay. Now, these points A, B, and C on this wave are at the exact same point in the waveforms as A, B, and C here at the top. So if we overlay these 2 waves, okay, on the same axis of time, then we have a difference of time, okay, a difference of distance. These things have traveled over that same period of time because of the way the waves are. Okay. I'm sorry, distance in time, not distance in not distance overall. They're at a different point in time. Okay. So if you look at this, this is basically when you look at one waveform, you go up, down, or 0, a minimum, and then back to 0. Okay, and the amplitudes. So each wave is 360 degrees. So if we take a look at this, when we get to the top, we're at 90, 180, 270, 360. Okay. We're also, if you talk about distance, we're at 1/4 wave, 1/2 wave, 3/4 wave, 1 full wave, okay, of distance. Okay. So now we look at this differential between this point and this point, which are on the same point of the waveform, but a different point in time. So that wave this wave is ahead by 1/4 of a wavelength in time, and it's also 90 degrees ahead of this same point here along the axis. Okay, so in the wave, it's 90 degrees ahead of where this one is. Okay, hopefully that makes sense. Again, these are all the same points on the waveform at different points in time. That's what we talk about when we're talking about phase. Okay, polarization is dependent on the directions of the line of force. We get a lot of questions about polarization. Is it, horizontal, vertical? What does it mean? Okay, so if the EM field, when you look at the EM wave and it's a big cross and you've got, your vertical portion is your electrical part of that EM wave, then it's vertically polarized. If we swap it, now it's the horizontal portion and it's parallel to Earth, it's horizontally polarized. Now, as waves travel through the atmosphere, they get kind of turned and bumped, and you'll end up with an elliptical polarization where you have part of it's vertical, part of it's horizontal, and it turns into an ellipse. You can also build an antenna specific so that it rotates 360 degrees, that field, over one wavelength, and you get a circular polarization. But For our purposes here, we're going to talk about horizontal and vertical polarizations, and that's it. Okay, but I just want you to understand it's dependent upon the electrical part of that wave. Okay, field intensity. It's a measurement of the strength of the wave at a distance from the radiating point or the antenna. Okay, so when we go downfield from the antenna, this wave's propagating. We want to know how strong that wave is. That's its field intensity. And it's measured in voltages between 2 points on the wavefront. For radio waves, typically we're talking about millivolts and microvolts of field intensity, not full volts. Okay, and it varies inversely to the distance. So basically, if you have just for numbers, a 100 millivolt per meter field intensity at 100 meters away from the antenna, it's going to half itself when you double the distance. Okay, so it would be 50 millivolts at 200 meters. Okay, so field intensity also relates to power density. Okay, so we start talking about power density. Power density is just basically equating the energy in that wave from field intensity to power. So not talking about voltage, we're talking about actual power, and that requires you knowing the impedance of the air. So that would be, and that's in free space, it's 377 ohms. It's pretty much a constant. Okay, so you would take the voltage and divide it by the resistance, and that gives you power, and that's going to be measured in milliwatts or micro watts per meter squared. Okay, just a little aside, we're not really going to talk into power density a whole lot, but I wanted you to understand that it's related to intensity in case somebody talks to you about power density and field intensity, that they're related. And basically those two are related by the power formula. The field intensity, or I'm sorry, the power density, it varies by the square root of the distance. Okay, the square of the distance, excuse me, as it travels away. So if power density is 4 milliwatts at meters per squared at 100 meters, it's going to be 1 milliwatt at 200 meters. So you start taking the square of the distance. Okay, so when you double it, it's gonna, you double the distance, it's gonna take it by the square. So you have those losses over time, and those losses, okay, over distance is attenuation. I know that's a long way to get around to attenuation, but basic, it's the loss of the power density or the field intensity as the wave propagates away from the antenna. Okay, we lose power as we go away, and that's attenuation. So you'll learn more about that as we go. But keep in mind, when we talk about attenuation, there's mathematical attenuation, then there's real world attenuation. Okay, because we know point A to point B is not always a clear, straight shot of free space or vacuum. There'll be trees in the way, there'll be buildings in the way. The atmosphere plays part of it, how propagation is with the atmosphere. So your attenuation of that signal is going to vary due to absorption. It's going to vary due to, the objects in your way. It's going to deal with refraction, reflection. So there's very, very, very many variables that come into play when you're talking about attenuation. So your theoretical or mathematical attenuation can be very different from your real world attenuation. Okay, so now we've completed the fundamentals of electromagnetic waves. We're time to move on now to the characteristics and fundamentals of antennas. That'll be the next video, and then we'll get into some design stuff. So please, I hope you found this entertaining and informational, educational. Hit the subscribe button and the like button. It helps us with the algorithm so we can also educate other folks on amateur radio and let people find us and other hams find us. So we'd appreciate that. Also hit the notification button so you can get the notifications when the next couple videos in this series come out. and anything else we do here from the Ham Shack. With that, I will say 73. Stay healthy, stay safe, stay passionate about amateur radio because it is the best damn hobby on the planet, and you know I'm passionate about it. So with that, from the Ham Shack, NJ4Z, I'm out.